Hello there, and welcome to the Sleepy Science Secrets. Tonight, we are going to travel somewhere extraordinary. We are going to find out why the most beautiful structures in the entire universe, structures so large they contain hundreds of billions of suns, structures so ancient they were already turning before our world even existed, why those structures curl, why they spiral, why the universe, when it gathers enough of itself together in one place, tends to arrange itself into something that looks almost like a seashell or a fern uncurling in spring, or the slow pull of water disappearing down a drain on a quiet morning. The spiral shape appears everywhere in nature, from the tiniest nautilus shell resting on a beach to galaxies so enormous that light itself takes 100,000 years just to cross from one side to the other. And the reason, the deep, soft, scientific reason, turns out to be one of the most calming stories the universe has ever told about itself. It is a story about spinning and patience and invisible waves moving through rivers of stars, and the way order arises gently and inevitably from the simplest possible beginnings. So settle in. Let your body find its heaviness. Let the ceiling above you become the night sky. We are going somewhere very far away, and we are going very slowly. Imagine you are floating in space, not falling, not drifting in any anxious way, just suspended in a vast and perfectly silent dark. There is no temperature here, no wind, no sound. Only the faint, ancient light of distant things traveling toward you from every direction at once. You are not cold. You are simply still, and the universe is doing what it always does around you, turning, building, patient, and unhurried as it has always been across all the billions of years of its existence. From here, if you let your eyes adjust to the dark, the way eyes do, when a room slowly becomes familiar, you would begin to make out shapes. Enormous shapes, impossibly far away, each one glowing with the combined light of hundreds of billions of individual suns. Some are round and soft, like eggs of pale gold. Some are small and irregular, without any particular form. And some, the ones that hold tonight's story, are flat and curling, shaped like slow pinwheels, like smoke rings turning in still air, like the most patient whirlpools you have ever imagined. These are the spiral galaxies, and they are waiting for you to ask why. The story of why galaxies form spirals begins at the very beginning, not the beginning of galaxies specifically, but the beginning of everything, when the universe was young and hot and filled with almost nothing except hydrogen and a little helium, the two simplest and lightest elements that exist. You can think of the early universe as an enormous, unimaginably hot fog, dense and bright and featureless, with no stars yet, no planets, no structures of any kind. Just energy and the simplest atoms, spread nearly uniformly in every direction, nearly uniformly but not perfectly, and that tiny imperfection, that almost imperceptible unevenness in the distribution of matter in the early universe, is where tonight's story begins. Because it is from those tiny variations, those faint wrinkles in the fog of the early cosmos, that everything you will ever see eventually grew. In the moments after the universe began cooling, those small regions of slightly higher density began to do what denser regions always do. They attracted more material. Gravity, that most persistent and patient of forces, began pulling gas toward the places where gas was already slightly thicker. Slowly, the fog began to develop structure, filaments formed. Vast threads of gas, hundreds of millions of light years long, with emptier regions between them, began to outline the large-scale architecture of the universe. And at the intersections of those great filaments, where the threads crossed and material pooled, something special began to happen. Gas began to gather in enormous concentrations. Not quickly. Nothing in this story happens quickly, but steadily. Over millions upon millions of years, vast clouds of hydrogen began to collect, drawn together by their own gravity, in the places where the universe was, for whatever reason, just slightly richer to begin with. These clouds are called protogalactic clouds, which is simply a name that means the cloud of gas that a galaxy will eventually become. Each one is unimaginably large, often tens of thousands of light years across. Each one contains more matter than any human concept of large can comfortably hold. And each one, at this point in its story, is doing something extremely simple. It is falling. Not downward in the way rain falls, but inward toward its own center of mass, pulled by the gravity of all its own material, gathering toward the middle. The cloud is, very slowly and very peacefully, beginning to collapse. Now, here is where the spiral begins to whisper its first note. Almost every large cloud of gas in the universe has, by some small accident of its history, a faint rotation. Perhaps a neighboring cloud nudged it gravitationally as it passed by in the cosmic dark long ago. Perhaps it inherited a slight spin from the turbulent conditions of the early universe. It does not matter exactly where the rotation came from. What matters is that it is there, barely detectable, almost nothing, like the almost imperceptible rotation of a leaf settling onto the surface of a still pond. But it is there, and as the cloud begins to fall inward, that tiny rotation is going to become the most important thing about it. You may have seen a figure skater pull her arms in toward her body during a spin and watched her suddenly accelerate, turning faster and faster the more compact she becomes. This is not a trick or a coincidence. It is a law of physics, one of the most fundamental and graceful laws the universe has, called the conservation of angular momentum. It means, in simple terms, that when a spinning object gets smaller, it spins faster. The spin is preserved. It is concentrated. It cannot simply disappear. And so, as the protogalactic cloud begins to collapse inward under its own gravity, growing smaller and denser, the faint original rotation it carried begins to increase. Slowly at first, then faster. The cloud, once barely turning at all, begins to spin with purpose. As the spinning increases, something else happens, just as gently and inevitably. The spin pushes outward, in the plane of rotation, resisting the collapse in that direction. Gas can still fall inward along the axis of rotation, collapsing freely from above and below the spinning plane. But in the equatorial plane, the spinning motion pushes back against the infall. The result is that the cloud, instead of collapsing into a sphere, collapses into a disk, a flat, rotating disk of gas, growing thinner and more defined over millions of years, like a slow breath being held. The disk is the foundation of the galaxy. Everything that will eventually become the beautiful spiral shape you see in photographs, every star, every arm, every ribbon of glowing dust, all of it will emerge from this quietly spinning disk. Let the image of that disk rest in your mind for a moment. It is perhaps 100,000 light years across, impossibly thin in proportion to its width, spinning in the dark like a slow record in the deep silence of space. It is mostly hydrogen still, cool, dark hydrogen in the outer regions, warmer and denser hydrogen closer to the center, where the collapse has been most complete. And already, in its denser regions, stars are beginning to switch on. The first stars of the new galaxy are igniting like embers catching in a slow fire, and their light is the first light the galaxy has ever made from its own material. This is one of the quietest and most extraordinary moments in the universe's long history. A new galaxy waking up. If you are resting comfortably right now, this might be a lovely moment to like the video. It helps the channel reach other quiet evenings, other people looking for something soft before sleep. And if you have not yet found the playlist, it is there, waiting for you, full of other slow journeys like this one. Inside the new disk, the stars that form begin to orbit the galactic center, each one following its own path, pulled by the gravity of all the material inside its orbit. Stars closer to the center move faster, completing their orbits in a shorter time. Stars farther out move more slowly, taking longer to complete the loop. This is the same principle that governs planets around a star. The inner ones move fast, the outer ones move slow. And it applies just as gracefully to stars orbiting the galactic center. In the language of astronomers, this is called differential rotation, different parts of the disk rotating at different speeds. And differential rotation is the next ingredient in the recipe for the spiral shape. If you had a disk of evenly distributed gas and stars, and you set it rotating with this differential speed, faster in the middle, slower at the edges, and then you marked a straight line of material from the center outward and watched what happened over millions of years, you would see that line gradually curve. The inner part of the line, moving faster, would pull ahead. The outer part, moving slower, would fall behind. And the line would begin to curve into a graceful arc, exactly the shape of a spiral arm. This purely mechanical process, the winding of material by differential rotation, was once thought to be the entire explanation for spiral arms. But it turned out to create a problem. If it were that simple, the arms would keep winding tighter and tighter over billions of years, eventually winding up completely and leaving no spiral pattern at all. The galaxy would smooth itself out. And yet, we look out at the universe and see beautiful, open spirals everywhere, many of them billions of years old, their arms still gracefully curled. Something else must be maintaining the pattern. That something else is one of the most elegant ideas in the whole of modern astronomy, and it is called the density wave theory. The idea is this: the spiral arms of a galaxy are not made of specific stars or clouds of gas that are locked together and traveling through space as a unit. Instead, they are patterns, waves of higher density moving through the disk of the galaxy, the way a wave moves through water. The water itself does not travel with the wave. It rises and falls as the wave passes, and then returns to where it was. The wave is a pattern in the water, not a piece of it. In a galaxy, the density wave moves slowly through the disk, sweeping around the galactic center over a time scale of hundreds of millions of years. As the wave passes through a region of the disk, it slightly compresses the gas and dust there. The way a gentle pressure at the back of a crowd causes the people in the crowd to bunch up momentarily before continuing on their way. The stars in the disk pass through this zone of higher density, slow down just slightly as they enter the denser region, spend more time there, and then emerge on the other side and continue their orbit. Because stars spend more time in the denser region, the region appears brighter. There are more stars there at any given moment, even though the stars themselves are always moving through it. The arm is an effect of the wave. It is a traffic jam in space, in the most peaceful and beautiful sense of that phrase. And the compression of gas in the density wave does something extraordinary. As the gas clouds enter the denser region and are compressed, they reach the threshold needed for collapse. New stars begin to form, large, hot, brilliant stars that burn blue-white with tremendous brightness. These young stars outline the spiral arm from within, tracing the path of the density wave with their own newborn light. This is why spiral arms appear brighter than the regions between them. They are places where new stars are constantly being born, lit up along the edge of the way foam outlines a wave on water. Between the arms, things are quieter. The stars are older, cooler, redder. They have been burning for longer. They remember the arm they were born in, now far behind them in their orbit. You can breathe slowly with that image. The spiral arm as a birthplace, a place where the compression of ancient gas becomes new light, over and over, as the wave moves through the galaxy with the patience of something that has all of time to spend. The Milky Way has been making new stars this way for nearly 10 billion years. It will likely continue for billions more. Our own galaxy, the Milky Way, is a barred spiral galaxy, which means that its spiral arms do not emerge directly from the very center, but instead spring from the ends of a long straight bar of stars that stretches across the central region, like a rod of light with arms reaching out from both ends. This bar is thought to span about 27,000 light years across the center of the galaxy, and it rotates with the rest of the disk, though not quite in the same way. The bar structure forms through a process called resonance, a beautiful word for a beautiful idea. Certain stars at certain distances from the center have orbital periods that are in a simple mathematical relationship with the speed of the spiral pattern rotating through the disk. These resonances gradually organize the stars into elongated, non-circular orbits that collectively produce the bar shape. It is spontaneous self-organization, order arising from the simple repetition of orbital mechanics, the way a chord is more than the sum of its notes. The Milky Way has 4 major spiral arms. They are named after the constellations in the areas of Scuae, where they are most visible from Earth: the Perseus arm, the Sagittarius arm, the Centaurus arm, and the Norma arm. Our solar system lives in a smaller structure called the Orion arm, sometimes called the local spur, a partial arm or spur that lies between the Sagittarius and Perseus arms, like a quieter lane on a winding road. We are not in one of the major arms. We are in a gentler, less crowded region, which perhaps gives us a slightly clearer view of the arms on either side, though the dust between us and them makes looking through the galactic plane in visible light quite difficult. Because we live inside the Milky Way, understanding its structure is, in some ways, harder than understanding the structure of galaxies far away. It is a bit like trying to understand the layout of a city from inside one of its buildings. We cannot simply look down at the Milky Way from above and see its spiral arms spread out below us. We have to infer the structure from the inside by measuring distances to stars and gas clouds, by studying the motion of material throughout the disk, by using wavelengths of light like radio waves and infrared that can pass through the dust and give us a clearer picture. Our understanding of the Milky Way's spiral structure has been built up over decades of patient observation, and it is still being refined. There is something quietly wonderful about the fact that the galaxy we know least well in some respects is our own. Let your eyes stay closed, or nearly closed, and let the image of the Milky Way come to you, not as a scientific diagram, but as something felt, a vast, slow wheel of light, turning in the dark, carrying you and everything you have ever known along with it. Unhurried and certain, the center of the Milky Way is a remarkable and quietly strange place. It is about 26,000 light years from our solar system, so far that even light traveling at 300,000 kilometers per second takes 26,000 years to make the journey. The center is dense, with stars packed far more closely together than in our neighborhood of the galaxy. If you could somehow stand on a planet near the galactic center, your night sky would be staggeringly bright. Thousands of stars close enough to cast shadows, a blaze of light where we have darkness. It would be a very different kind of night. At the very heart of this central region sits something enormous and invisible, a supermassive black hole called Sagittarius A star, written by astronomers as SGRA-COS. It has a mass of about 4 million times the mass of our Sun, 4 million suns compressed into a region smaller than our solar system. It is not currently active in the way that some galactic centers are. It is, for now, in a quiet phase, not consuming large amounts of material, not blasting out the powerful jets of energy and radiation that active galactic nuclei are famous for. It is simply there, holding the center of the galaxy with its immense gravitational presence, the way a deep, quiet weight holds the heart of something in place. How do we know SGRA star is there, since it cannot be seen directly? Astronomers spent decades patiently watching the motions of stars very close to the galactic center, stars that orbit something invisible at tremendous speeds, completing their orbits in years rather than millions of years. The only thing that could make a star orbit so fast in such a small loop is something with enormous mass packed into a tiny region. The orbits of those stars around the invisible center are some of the most compelling evidence we have for supermassive black holes, and the scientists who tracked those orbits received the Nobel Prize in Physics in 2020. It was a discovery made entirely through patience, watching, measuring, waiting year after year to see where the stars went. Supermassive black holes like SEGR-A star are thought to play a role in shaping the galaxies they live in, not just passively sitting at the center, but actively influencing the rate of star formation through a process called feedback. During periods when the black hole is actively consuming material, it releases enormous amounts of energy, jets of radiation, and particles that stream outward from the central region and heat the surrounding gas, making it harder for that gas to cool and collapse into new stars. This self-regulating process, the galaxy's own engine controlling how fast it grows, is one of the many ways the universe achieves balance through opposing forces, like the way a fire warms the air around it until the warmth itself begins to slow the fire. Perhaps you would like to check the playlist. There are other quiet nights there, full of soft facts about deep time, ocean currents, the inner life of forests, the way light bends around massive things. Each one was made for a night exactly like this one. There is a concept in galaxy science called the Hubble sequence, which is simply a way of organizing galaxies by their shape, a visual classification system first proposed by Edwin Hubble in the 1920s. Hubble arranged galaxies along a diagram that looks a bit like a tuning fork. Elliptical galaxies on the left, ranging from nearly spherical to quite flattened, and spiral galaxies on the right, split into a normal spiral branch and a barred spiral branch, ranging from tightly wound with large bulges at one end to loosely wound with small bulges at the other. In this scheme, spiral galaxies are classified as SA, SB, or SC, or for barred spirals, SBA, SBB, or SBC. An SA galaxy has a large, bright central bulge and tightly wrapped spiral arms that are not very prominent. An SC galaxy has a small bulge and wide open, loosely wound arms with a great deal of visible structure, knots of star formation, dust lanes, brightness variations along the arms. The Milky Way is thought to be somewhere in the range of SBBC, a barred spiral with moderately open arms, somewhere between the tight and loose ends of the spectrum. Not too tightly wound, not too loose, a balanced, comfortable kind of spiral. The classification system Hubble devised was originally sometimes called the tuning fork diagram, and at first some astronomers mistakenly thought it represented an evolutionary sequence, that galaxies started as ellipticals and evolved into spirals, or vice versa. We now know this is not the case. Galaxies do not simply slide from one type to another. Elliptical galaxies and spiral galaxies form through different histories, different environments, different interactions with their neighbors. A spiral galaxy can, over billions of years, merge with another galaxy and become an elliptical. But it does not simply evolve from one to the other under quiet, undisturbed conditions. The shapes are records of history, of formation, environment, and the particular accidents of gravitational encounter that each galaxy has experienced. Edwin Hubble himself is a remarkable figure in the history of our understanding of the universe. Working at the Mount Wilson Observatory in California in the early 1920s, using the largest telescope in the world at that time, he measured the distance to the Andromeda Nebula, a fuzzy patch of light visible to the naked eye in the constellation Andromeda, and found that it was not a cloud of gas within the Milky Way, as many astronomers had believed, but a whole separate galaxy, enormously distant. This single discovery expanded the known universe overnight. Before Hubble's measurement, many scientists thought the Milky Way was the entire universe. After it, the universe became a place filled with billions of separate galaxies, each one an island of stars in an ocean of mostly empty space. The moment of that realization must have been something. To look at a fuzzy smear of light and understand for the first time that it was itself an entire universe of stars, all its own. The Andromeda Galaxy, which Hubble measured, is the closest large spiral galaxy to our own. It lies about 2.5 million light-years away, and the light you would see from it tonight left it 2.5 million years ago, when our earliest human ancestors were only just beginning to walk the African savanna. That light has been traveling toward you through the complete emptiness of intergalactic space for all of human history, and every history before that, and it arrives tonight at your eyes, still carrying in it the pattern of Andromeda's spiral arms, a little smeared by the distance, but real and present. Andromeda is slightly larger than the Milky Way. It contains somewhere in the region of 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion. It is also at this moment approaching us. Astronomers have measured its velocity and found that it is moving toward the Milky Way at roughly 110 kilometers per second. In approximately 4 to 5 billion years, the two galaxies will begin to interact gravitationally, and over several 100 million years following that, they will merge, passing through each other, separating, swinging back together, slowly combining into a single, larger galaxy. Most likely, the result will be an elliptical galaxy. The spiral structure of both the Milky Way and Andromeda will be gradually erased during the merger, the arms dispersed and mixed, the disk dissolved into the rounder shape of the merged system. This might sound alarming, but there is no reason to feel any unease about it. When galaxies merge, the individual stars separated by such vast distances within each galaxy almost never collide. The merger is almost entirely a gravitational event, not a physical one. It is more like two enormous soap bubbles drifting into each other than two solid objects colliding. The stars of the Milky Way and Andromeda will pass among each other like two clouds of fireflies. Many of them will be flung into new orbits. The galaxy will reshape itself. But the sun and any world still orbiting it 4 billion years from now will probably survive undisturbed, simply finding itself in a new position, in a new, larger galaxy. A galaxy that astronomers have informally nicknamed Milkomeda, which is perhaps the most gentle and friendly name for an event of cosmic proportions that has ever been devised. Let your breathing slow a little more now. We are going deeper into the night, and the galaxies are all around us, turning on their own time scales, unhurried by anything as small as a human lifetime. One of the most intriguing aspects of spiral galaxies, one that took astronomers by surprise when they first discovered it, and that has shaped our understanding of the universe in profound ways, is the way they rotate. When astronomers measured how fast different parts of spiral galaxies were moving around their centers, they expected to find a familiar pattern: fast rotation near the center, where most of the mass is concentrated, and increasingly slow rotation farther out. This is exactly what we see in our own solar system, where Mercury races around the Sun in 88 days, while distant Neptune takes 165 years. The outer parts, being farther from the concentrated mass at the center, should be moving more slowly. But that is not what they found. When astronomers measured the rotation curves of spiral galaxies, graphs showing the speed of rotation at different distances from the center, they found something unexpected. The speed of rotation in the outer parts of galaxies did not decrease with distance. Instead, it remained roughly constant, or even increased slightly, far out into the disk and beyond. Stars at the edges of galaxies were moving just as fast, or nearly as fast, as stars much closer to the center. This is not what you would expect if the visible stars and gas were all the mass there was. Something else must be present. Some additional mass distributed throughout the galaxy and beyond its visible edge, providing the extra gravitational pull needed to keep the outer stars moving so fast. That something is dark matter. It is called dark not because it is sinister or frightening, but simply because it does not emit, absorb, or reflect any light that we can detect. It does not interact with light at all. It interacts only through gravity. And yet, its gravitational effects are unmistakable. Every spiral galaxy we observe appears to be embedded in a vast halo of dark matter, a roughly spherical cloud of this invisible material extending far beyond the visible disk of the galaxy, perhaps 2 to 3 times its diameter, holding the galaxy in a gravitational embrace that keeps its outer regions spinning faster than they otherwise could. Dark matter is one of the great open questions of modern science. No one knows what it is made of. It is not made of atoms, as far as we can tell. Not hydrogen, not helium, not any of the familiar elements. Various theoretical candidates have been proposed. Exotic particles with names like WIMPs and axions. But none have yet been definitively detected in a laboratory. What we know about dark matter comes entirely from its gravitational effects on the rotation curves of galaxies, on the bending of light from distant objects, on the large-scale structure of the universe. It makes up roughly 27% of the total energy content of the universe, while all the visible stars, planets, gas, and dust, everything we can see with any telescope, makes up only about 5%. The universe is mostly invisible, and the beautiful spiral shapes we are talking about tonight are held together, in part, by something we cannot see and do not yet fully understand. There is something deeply peaceful about that thought, if you let it settle into you gently. The visible is cradled by the invisible. The light is held in place by the dark. The spiral turns within a halo of something quiet and permanent, and still not named. If you are finding this journey a soft and restful one, a like and a comment are always a gentle gift. They help this channel find its way to other quiet evenings, other people looking for something gentle before sleep. Let's rest with the idea of galactic interactions for a while, because when galaxies draw close to each other, the results are among the most beautiful things the universe produces, and they carry their own particular softness. When 2 spiral galaxies pass close to each other, not necessarily merging completely, but coming near enough that their gravitational fields overlap, the tidal forces between them can draw long, graceful streams of stars outward from both galaxies, stretching into space in sweeping arcs called tidal tails. These tails can extend for hundreds of thousands of light years, lit by the stars being drawn along them, and they give interacting galaxies a look of extraordinary elegance, as though the 2 galaxies are reaching toward each other, or perhaps exhaling slowly into the dark. A famous example is the pair of galaxies known as the antennae galaxies, located about 45 million light-years away in the constellation Corvus. They are named for the 2 long, curving tidal tails that extend from them in opposite directions, like the antennae of some vast and gentle creature. The two galaxies are currently in the early stages of a merger, and the collision of their gas clouds is producing intense bursts of new star formation. Thousands of young star clusters blazing bright, born in the turbulence of the encounter. The images taken of the antennae galaxies by the Hubble Space Telescope are among the most vivid and beautiful in all of astronomy. The chaos of the collision rendered as a tapestry of gold and blue and pink. New stars being born along the edges of the colliding gas, the tidal tails sweeping gracefully outward in opposite directions. Out of disturbance, new light. Another beautiful interacting pair is the Whirlpool Galaxy and its companion, a smaller galaxy called NGC 5195, located about 23 million light-years away in the constellation Canes Venatici. The Whirlpool, also known as Messier 51, is a grand spiral seen nearly face-on from Earth, with two well-defined broad spiral arms and a bright central nucleus. Its companion appears connected to one of its arms by a faint bridge of material, though astronomers now believe that the companion has actually passed behind the whirlpool, and its apparent connection to the arm is a projection effect. The gravitational interaction between the two has helped shape and amplify the whirlpool's spiral structure. The passage of the companion is thought to have triggered waves of star formation along the arms, brightening them and making their structure more defined. The whirlpool holds a special place in astronomical history. In 1845, the Irish astronomer William Parsons, the third Earl of Ross, observed it through his massive home-built telescope at Birr Castle in Ireland, at the time the largest telescope in the world. Looking through the eyepiece on a clear Irish night, he became the first person ever to recognize the spiral structure of a galaxy. He sketched what he saw, and the sketch shows the curling arms quite clearly. An extraordinary thing to have perceived through a telescope in the mid-19th century, through all the wobbling air and imperfect mirrors, the light from that distant galaxy arriving faint and small, and yet still clearly, unmistakably spiral. He used the word spiral to describe what he saw, and the word has not changed since. The universe gave the spiral shape its name on a cold night in Ireland in 1845, in the quiet grounds of a castle, through a brass eyepiece, by the light of a galaxy 23 million light-years away. There is something about that image that asks you to let go of ordinary time, to feel how long things have been happening, and how gently. Let your body sink a little deeper into wherever you are resting. The night is getting softer. The facts are becoming feelings. The distances are becoming a kind of rest. The spiral structure of galaxies is not just beautiful, it is functional, in the way that beautiful things in nature often are. The spiral arms, as we have discussed, are regions of ongoing star formation, where the compression of gas by the density wave triggers the birth of new stars. This has profound consequences for the chemical evolution of galaxies and, eventually, for the existence of everything in them. Stars are not just balls of burning gas, they are factories. Inside their cores, the intense heat and pressure of nuclear fusion takes simple hydrogen and helium and builds heavier elements: carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, iron, and dozens more. When a star reaches the end of its life, it returns much of this enriched material to the galaxy, either through gentle stellar winds in the case of smaller stars, or through the magnificent violence of a supernova explosion in the case of the more massive ones. This returned material, enriched now with the elements the star spent its life producing, mixes back into the gas of the galaxy and becomes available for the next generation of stars and planets to form from. Spiral galaxies, with their ongoing star formation in the density wave arms, are continuously cycling through this process. New stars form, live, die, enrich the gas. New stars form again. Each generation of stars is made of material slightly richer in heavy elements than the last. And it is from these heavier elements, the ones that can only be forged inside stars, that rocky planets are made, and oceans and atmospheres. And eventually, after billions of years of this patient recycling, living things, the carbon in your body was made in the core of a star. The oxygen in your lungs was made in the nuclear furnace of a star that ended its life perhaps billions of years before the sun was born. You are, in the most literal chemical sense, the product of spiral arm star formation, a thing the galaxy made from its own material, slowly, over an enormous span of time. There is a certain kind of peace in knowing that you did not arrive from somewhere outside the universe. You are the universe thinking about itself. The spiral turned for billions of years to produce the material that eventually produced you. And tonight, you are taking that material and resting it, which seems, in the grandest possible sense, exactly right. Spiral galaxies also contain the full record of their own history in their structure. The stars in the disk are generally younger, formed from material that had already been enriched by previous stellar generations. The central bulge contains many of the oldest stars, formed early in the galaxy's history when the protogalactic cloud was first collapsing and the first burst of star formation took place. The halo, the sparse, roughly spherical distribution of old stars and globular clusters that surrounds the disk, is older still, thought to represent the earliest phase of the galaxy's formation before the disk had fully settled. Reading a galaxy is, in a way, like reading tree rings. The oldest layers are on the outside and the center, and the newer growth is where the action currently is. Globular clusters are particularly poignant objects in this context. They are dense, spherical collections of tens of thousands to millions of very old stars, bound together by their mutual gravity into a compact, glowing ball. The Milky Way has over 150 of them, distributed in a roughly spherical halo around the galactic disk. They are the elders of the galaxy's stellar population, formed billions of years ago, before the disk even settled into its current shape. They move in slow, elongated orbits that take them far out into the halo and back through the disk, sometimes crossing the plane of the Milky Way once every few 100 million years. They have been doing this for longer than the sun has existed. They are quiet and they are ancient, and they carry in their stars the chemical memory of the very early universe. When you look at a globular cluster in a long exposure photograph, a dense sphere of light, each point in it a sun, it looks like a handful of salt scattered on velvet, or like a city seen from very high above on a clear night, all the lights close together and steady, or like a very old dream that the galaxy has been having for 10 billion years and has no intention of waking from. Please check the playlist if you have not already. There are other slow journeys there with the same soft pace as tonight. And if someone comes to mind who might enjoy falling asleep under the stars, the channel is always glad to have quiet company. There are more than 2 trillion galaxies in the observable universe, a number determined through careful analysis of deep field images taken by the Hubble Space Telescope. Images that peer back nearly to the beginning of cosmic time, showing galaxies in their earliest forms when the universe was only a few 100 million years old. 2 trillion. The number is so large that it is more useful as a feeling than as a figure. The feeling it produces, if you let it in gently, is something like deep security. The sense that the universe is so rich, so full, so endlessly productive, that no particular thing in it is lonely or accidental. Every star, every galaxy, every quiet disk of gas turning in the dark is part of a tapestry so vast it has no edge that we can see. Of these 2 trillion galaxies, a significant fraction are spirals, perhaps a third of all large galaxies, and a higher proportion when you look at galaxies similar in mass and age to the Milky Way. The universe has a fondness for the spiral. It arrives at it through physics, through angular momentum and differential rotation and density waves. But the result has a quality that physics does not usually claim. It is beautiful. Not incidentally beautiful, not beautiful only to human eyes, trained by millions of years of evolution to find certain patterns pleasing. It seems beautiful in a more structural sense, because it is the shape that physics arrives at when it has had enough time, enough space, and enough material to settle into its most natural form. There are galaxies that have lost their spiral structure. Elliptical galaxies, those smooth, rounded collections of mostly old stars, are thought in many cases to be the remnants of spiral galaxies that have merged. The merger disrupts the disk, scatters the stars into random orbits, and over billions of years the merged system settles into the smooth, featureless elliptical shape. Ellipticals tend to contain older stars, show little ongoing star formation, and are found preferentially in the dense centers of galaxy clusters, where interactions between galaxies are more common. They are quieter than spirals. They have already passed through their most active phase. They are, if galaxies can be said to have states, resting. Perhaps there is something right about that too. Things that have been active for a very long time eventually become still. The spiral turns and turns and turns, making new stars cycling through its arms, and then, after a very long time, after an encounter with another galaxy has stirred it beyond the recovery of its shape, it settles into the rounded piece of the elliptical, still glowing, still full of stars, just no longer turning in the same way, just resting. Your breathing might have slowed considerably by now. That is good. The night is doing what it is supposed to do, and you are doing what you are supposed to do, and somewhere above the ceiling and the clouds and the atmosphere, the galaxy is doing the same. Let us spend a little time with the scale of things, because there is a kind of meditation in scale, a way that very large numbers, if you let them pass through you gently enough, can dissolve the ordinary anxieties of a human day into something that feels very small and very manageable. The Milky Way is approximately 100,000 light years in diameter. A light year is the distance light travels in 1 year, moving at 300,000 kilometers per second, about 9.5 trillion kilometers in total. So, the Milky Way is roughly 950 quadrillion kilometers across. If you tried to drive across it in a car traveling at 100 kilometers per hour without stopping, it would take you about 10 billion years. The universe itself is only about 14 billion years old. The car would not make it. The thickness of the Milky Way's disk in the region where the Sun lives is about 1,000 light years. The disk is very thin in proportion to its diameter, like a record, or perhaps thinner. A vinyl record is about 4 millimeters thick and about 30 centimeters in diameter, a ratio of roughly 1 to 75. The Milky Way is roughly 1 to 100 in the same ratio, even thinner than a record. A flat, spinning disk of stars, impossibly thin in proportion to its width, turning in the dark. The distance from the Sun to the center of the Milky Way is about 26,000 light years. Light from the galactic center has been traveling toward us since before modern humans existed, before the last great ice age, before the extinction of the mammoths, before the earliest cave paintings were made on the walls of caves in Europe and Africa. And it is still traveling. It will arrive here in another few hundred years. The light we receive from the galactic center tonight left it thousands of years ago, carrying with it information about a place we will never visit and can only infer. The solar system takes about 225 to 250 million years to complete one full orbit around the galactic center. Astronomers call this a galactic year or a cosmic year. Since the Sun formed about 4.5 billion years ago, it has completed roughly 18 to 20 of these orbits. In that time, it has traveled through different regions of the galaxy, passed through different spiral arms, experienced different densities of surrounding material. Our solar system is ancient by human standards, but it has only lapped the galaxy a handful of times. The galaxy is patient in ways that are beyond calculation. You do not need to hold any of these numbers. They are not for holding. They are for softening you. They are for making the edges of your ordinary thoughts a little less sharp, the way a long view from a high place makes you feel both very small and very free. There is a question that often arises quietly when people think about the scale of galaxies. Are we alone in ours? It is a question that has no certain answer yet, not in the way that questions about spiral structure or dark matter have answers, built from careful measurement and a century of accumulating observation. But it is a question the science of galaxies has something gentle to say about. The Milky Way is rich in planets. We know this from the discoveries of the past few decades, from telescope missions like Kepler and TESS, which have shown that most stars have planets, and that many of those planets are rocky, and that many of them orbit at distances from their stars where liquid water could, in principle, exist. Estimates suggest there may be something like 100 billion planets in the Milky Way alone, 100 billion worlds, some of them warm, some of them wet, some of them old enough that, if life arose on them, it has had billions of years to develop into whatever it might become. We do not know if any of them carry life. We have not yet found a signal, a signature, a sign. But the numbers suggest that the question is not absurd. that in a galaxy as rich, as old, and as fertile as ours, the conditions for life appear to be present in abundance. Whether life actually arises when conditions are right, how often, how complex it grows. These are questions that remain open, held in the same gentle suspension as the question of what dark matter is, and why exactly the spiral wave maintains its shape across billions of years of galactic rotation. The universe holds its mysteries quietly, without urgency, and it does not seem to mind that we are still working on them. And you do not need to work on anything tonight. The questions will be there in the morning, patient as galaxies. The spiral arms of the Milky Way are not just places where new stars are born. They are also places where new solar systems form, complete with planets and moons, and, in at least one case we know well, oceans and sky and evening and a planet that tilts on its axis and has seasons, and nights when the sky is clear and the light from distant galaxies comes down through the dark to land on closed eyes. Our solar system formed about 4.5 billion years ago from a collapsing cloud of gas and dust in what was then an arm of the Milky Way, enriched by the deaths of earlier stars, containing all the elements needed for rocky planets and water and eventually life. The sun ignited at the center of the collapsing cloud, and the remaining material flattened into a disk, just as the protogalactic cloud had flattened into the galactic disk long before. And from that disk, over millions of years, the planets assembled themselves piece by piece, grain by grain, by the same physics that shaped the galaxy shaped the solar system: angular momentum, differential rotation, disk formation. The universe does not have many different tricks. It has a few very deep ones, and it uses them at every scale. Earth formed about 4.5 billion years ago. For the first several 100 million years, it was a hot, turbulent place, frequently impacted by other bodies, its surface covered in molten rock, its sky thick with volcanic gases. Then it cooled. The first oceans formed. And somewhere, we do not know exactly where or exactly when, the first living things appeared. Simple, single-celled, without any intention or awareness, but alive. And from that beginning, in the 4 billion years since, life has diversified into the extraordinary variety that fills the oceans and the forests and the soil and the air of this planet today, including a species that builds telescopes and points them at distant galaxies and asks why they curl. You are the galaxy asking itself a question, and tonight, having asked it and heard a long, soft answer, you are going to rest. We have traveled a long way together, from the very beginning, when the universe was nothing but a hot fog of hydrogen drifting in the primordial dark, all the way to the density waves and dark matter halos and globular clusters and tidal tails of the galaxies we see today. We have passed through the winding problem and the conservation of angular momentum, through the bar of the Milky Way and the rotation curves that revealed the invisible presence of dark matter. We have visited the galactic center and its patient, quiet black hole. We have spent time with Andromeda and the whirlpool and the antennae, with the cold Irish night, when a man first drew what he saw through a great telescope and wrote the word spiral beside it. We have been carried through the idea that you, your atoms, your molecules, your particular and irreplaceable arrangement of matter, are the product of all this, of spiral arms compressing gas into new stars. of those stars forging heavy elements in their cores, of supernovae scattering those elements back into the galaxy, of new clouds collapsing and new solar systems forming, and one small warm planet eventually growing something that can lie down in the dark and think about where it came from. You came from the spiral. The spiral came from a cloud. The cloud came from a fog. The fog came from the beginning. And the beginning, still quiet, still unfolding, still gentle in its enormity, is all around you right now, in the form of the universe that has never stopped being patient with everything it has made. Let your eyes close all the way now. Let the galaxy turn without you for a while. It will, and gladly, the same way the earth turns under you as you sleep, carrying you through the dark without asking anything in return. The spiral arms are out there, sweeping slowly through the disk of the Milky Way, compressing ancient gas into new light. The density wave moving through the material of the galaxy, the way a whisper moves through a quiet room. Stars are being born right now in the Orion Arm, in the Perseus Arm, in all the star-forming regions where gas has been compressed just enough to tip into collapse. New suns are lighting up in the dark, each one surrounded by its own disk of material, each disk perhaps already beginning to assemble its own worlds. There is something that happens in the deepest part of the night. Not a sound exactly, but a quality of stillness that settles over everything like the finest possible dust, like something the air does when it has finally finished moving. You may have noticed it before in those moments just before sleep arrives fully, when your thoughts begin to lose their edges and the ordinary world becomes something softer and less insistent. The scientists who study galaxies know a version of this feeling too, the particular stillness that comes from having looked at something so vast and so old that the ordinary scale of things simply dissolves. They sit in their offices with their data and their photographs and their models of rotating disks. And sometimes the numbers stop being numbers and become something else, become the feeling of standing at the edge of a very wide, very calm lake in the early morning, with the mist still on the water and no one else awake yet. That is the feeling we are going to stay inside for a while longer, because the story of spiral galaxies has more soft layers to it, more quiet rooms to pass through before we reach the deepest rest. We left you spinning slowly with the Milky Way, held in the galaxy's dark embrace, carried through space at extraordinary speeds you cannot feel, surrounded by hundreds of billions of stars, each doing their own slow work of burning hydrogen into helium in their cores, patient as the oldest possible lanterns. Let us begin this part of the journey with something closer than Andromeda, closer than the spiral arms we have been visiting. Let us begin with the particular neighborhood of the galaxy that our solar system calls home, and the quiet facts that make it a remarkable and gentle place to be. The region of the Milky Way where we live is sometimes called the galactic habitable zone, a phrase that borrows its logic from the idea of a habitable zone around a star, the region at the right distance for liquid water to exist on a planet's surface. The galactic habitable zone is the region of the Milky Way thought to be most favorable for the development of life, far enough from the turbulent, densely packed galactic center that the radiation environment is not too harsh, and close enough to the center that the interstellar gas has been sufficiently enriched with heavy elements by previous generations of stars. Too close to the center, and intense radiation and gravitational disturbances make stability difficult. Too far out in the sparse outer disk, and the gas is too thin and too poor in heavy elements for rocky planets to form easily. Our solar system sits in what appears to be a comfortable middle region, not too hot, not too cold, not too crowded, not too empty. A quiet corner of a large and varied galactic neighborhood. The interstellar medium, the gas and dust that fills the space between stars in the Milky Way's disk, is not a uniform thing. It has its own complex structure, its own phases, its own geography. There are cold, dense molecular clouds, the birthplaces of stars, where temperatures can fall to just 10 degrees above absolute zero, where the gas is thick enough to block the light of stars behind it, forming the dark patches you can see even with the naked eye in photographs of the Milky Way. There are warm regions of diffuse hydrogen, gently ionized by the ultraviolet light of nearby stars, glowing faintly red in long exposure photographs. There are hot bubbles of nearly empty space, carved out by the shock waves of supernova explosions. Regions where a star once died spectacularly and left behind an expanding shell of hot, fast-moving gas that has pushed the surrounding material outward, creating a cavity in the interstellar medium that can persist for millions of years. Our solar system, as it happens, sits inside one of these bubbles, a region of unusually low-density, hot interstellar gas called the local bubble, which extends for roughly 300 light-years in most directions around us. The local bubble was probably created by a series of supernova explosions that occurred in the neighborhood over the past 10 to 20 million years, blowing away the surrounding gas and leaving us in this relatively empty, quiet region. It is, in a way, a space that was cleared for us by the deaths of stars, a quiet room in the galaxy, swept clean by ancient explosions, in which our solar system has been able to go about its business without too much interference from the dense and active regions of the spiral arms nearby. There is something unexpectedly cozy about that image, the local bubble as a kind of cleared space, a quiet neighborhood in the larger city of the galaxy, where the nearest dense gas is far enough away that the night sky is mostly transparent, and the stars that do exist nearby are spread out comfortably, each one at a respectful distance from its neighbors. The nearest star to our sun is Proxima Centauri, at about 4.2 light-years, a distance so large that even the fastest spacecraft humans have ever built would take thousands of years to reach it. But in galactic terms, it is a neighbor. In galactic terms, the stars around us are all in the same small community, sitting in the same bubble, sharing the same quiet corner of the Milky Way. If you feel warmly toward tonight's journey, a like on the video is a quiet and generous thing. It costs nothing and carries the channel further into the world, which is always appreciated from the heart. Let us move outward now, past the local bubble, past the Orion Arm, out toward the edges of the Milky Way's disk, because the edges of spiral galaxies are their own kind of wonder, and they carry a softness that is different from the brightness of the arms. The outer disk of the Milky Way is a sparse and quiet place. The density of stars decreases as you move outward from the galactic center. There are fewer of them per unit volume, and they are spread more thinly across the disk. The interstellar gas also becomes thinner and less enriched with heavy elements because it has been processed through fewer generations of stars. In the outer disk, you are in a part of the galaxy that has always been quieter, always been less active, always seen fewer new stars born. The stars that do exist there tend to be older, formed earlier in the galaxy's history, burning quietly and slowly on the fuel they have had for billions of years. At the very edge of the disk, the boundary between the galaxy and the intergalactic medium is not sharp. It is gradual, a slow thinning, a progressive dimming, the way the light fades at the edge of a campfire's reach, not stopping abruptly, but becoming less and less, and eventually becoming something you are no longer sure of. The disk blurs into the halo, and the halo extends outward into the dark matter envelope that surrounds the galaxy. And the dark matter envelope eventually gives way to the vast, nearly empty spaces between galaxies, the intergalactic medium through which even the density of atoms falls to almost nothing. The intergalactic medium is not completely empty. It contains an extraordinarily diffuse gas, mostly ionized hydrogen, spread so thinly that there is perhaps only one atom per cubic meter, compared to the millions of atoms per cubic centimeter in the air you are breathing right now. This gas fills the enormous spaces between galaxy clusters, which can be hundreds of millions of light years across. It is one of the emptiest things in the universe, and also one of the largest. Most of the volume of the universe is this: nearly nothing, spread across distances that make the size of the Milky Way seem intimate and small. And yet, even this vast near emptiness is threaded with structure. The large-scale architecture of the universe, sometimes called the cosmic web, consists of great filaments of matter connecting galaxy clusters, with vast voids between them where almost nothing exists. The galaxy clusters sit at the intersections of the filaments, like knots in an enormous three-dimensional net. And within those clusters, the individual galaxies, spirals and ellipticals and irregulars, orbit each other, interact, sometimes merge, each one a small, bright knot of stars in a much larger pattern. The Milky Way is part of a small cluster called the local group, which contains about 50 to 80 galaxies, mostly small irregulars, with the Milky Way and Andromeda as the two dominant spirals. The local group is itself part of a larger structure called the Virgo supercluster, which is part of an even larger structure called the Laniakea supercluster, a vast flowing system of galaxies discovered only in 2014, stretching over 500 million light years and containing the mass of 100 million billion suns. You are resting tonight in a particular small, warm room of the Laniakea supercluster. That is not a scientific fact you need to carry around with you. It is more of a feeling to let pass through you like warmth, like the sensation of a very large, very quiet space in which you are entirely and permanently welcome. Let the breath slow. Let the body be heavy. There is more to tell, and it arrives softly. One of the most fascinating things about spiral galaxies, one that connects the very large and the very small in a way that feels almost like a whisper from the universe about its own consistency, is the way that the same mathematical patterns appear at wildly different scales in nature, and the spiral is perhaps the most conspicuous of them. The logarithmic spiral, the specific mathematical shape that most galaxy spiral arms approximate, is not unique to galaxies. It appears in the chambers of a nautilus shell, in the arrangement of seeds in a sunflower, in the unfurling of a fern frond, in the swirl of water going down a drain, in the pattern of a hurricane seen from above. This specific spiral, the one where the rate of turning and the rate of outward expansion are in a constant ratio, so that the spiral looks the same at any scale, seems to emerge wherever growth and rotation interact. It is the shape that things take when they are expanding outward while simultaneously turning. A nautilus shell grows its spiral because the organism adds material to its shell at a constant rate, while the whole structure rotates around a central axis, the same basic physics in a very different context as a galaxy building its arms. A sunflower's seeds spiral outward because that arrangement allows the most seeds to be packed efficiently into the flower head, and the specific angle that achieves maximum packing is related to a fundamental mathematical constant called the golden ratio. The spiral of a hurricane happens because the Coriolis effect, the influence of Earth's rotation on moving fluids, causes air flowing inward toward the low-pressure center to spiral rather than simply converge. In each case, the spiral is the solution that a physical system finds when it needs to reconcile inward flow with rotation. The universe, at every scale, arrives at the same answer. There is deep comfort in this consistency. The laws of physics are the same everywhere, in the spiral arm of the Milky Way and in the whirl of a fingerprint, in the orbit of a planet and in the curl of a wave. The universe runs on one set of rules, and those rules produce patterns that repeat across every scale, from the subatomic to the cosmic. You carry in your own body, in the spiral of your inner ear, in the double helix of your DNA, in the whirls at the tips of your fingers, the same mathematical signature that is written across the arms of galaxies. The universe is not random. It is deeply, quietly coherent. Your breathing has already found its own slow rhythm by now, without you having to think about it. Let it continue. The body knows what to do. The galaxy knows what to do. Everything is finding its way. Let us think for a while about light, specifically about the light that comes from spiral galaxies, and what it tells us, and how extraordinarily much information can be carried in something as insubstantial as a beam of photons crossing billions of light years of empty space to land on a detector the size of your hand. When astronomers observe a spiral galaxy, they do not just measure how bright it is. They split its light into a spectrum, the full rainbow of wavelengths from ultraviolet through visible light and into infrared. And they read that spectrum the way a doctor reads a set of test results, finding in it a wealth of information about what the galaxy is made of, how hot its stars are, how fast it is moving toward or away from us, and even how fast it is rotating. Different elements absorb and emit light at very specific wavelengths, a kind of fingerprint that no other element shares. Hydrogen absorbs light at a set of precise wavelengths called the Balmer series. Calcium has its own set. Iron has its own. When astronomers see these absorption lines in the spectrum of a galaxy, they know what the galaxy contains. But they also notice something else. The wavelengths are often shifted. Lines that should appear at one wavelength appear at a slightly different one. stretched toward the red end of the spectrum if the galaxy is moving away from us, compressed toward the blue end if it is moving toward us. This is the Doppler effect, the same phenomenon that makes a passing ambulance's siren change pitch as it goes by. And by measuring this shift in the light from different parts of a galaxy, astronomers can map out the galaxy's rotation, measure how fast the stars on one side are moving toward us, and how fast the stars on the other side are moving away, and from that deduce the full rotation curve that revealed decades ago the presence of dark matter. All of that information, the composition, the temperature, the velocity, the rotation, encoded in light, in photons that have been traveling for millions or billions of years, carrying their information perfectly preserved through the vacuum of space, not degrading or forgetting until they reach a telescope mirror and are reflected into a detector and become, finally, a number in a database on a hard drive in an observatory somewhere, and then a point on a graph, and then an insight, and then a story that is told on a quiet night to someone lying in the dark. The light has been patient. It always is. Do check the playlist if you feel like continuing this gentle journey on another night. There are other stories there, told at this same slow pace, about the deep ocean and the life inside mountains and the way the universe counted its own age from the light of ancient stars. There is a kind of galaxy we have not talked much about yet, the irregular galaxy, and it deserves a moment of quiet attention, because irregular galaxies are in some ways the most honest expression of what galaxies look like when the universe has not had time to organize them, or when two galaxies have recently disturbed each other beyond the recovery of either's original shape. The Large Magellanic Cloud and the Small Magellanic Cloud are two irregular dwarf galaxies visible to the naked eye from the southern hemisphere, two faint cloud-like patches in the southern sky that look from a distance like detached pieces of the Milky Way that have drifted away. They are, in fact, satellite galaxies of the Milky Way, orbiting our galaxy at distances of about 160,000 and 200,000 light-years, respectively. Both are irregular in shape. The Large Magellanic Cloud has some hints of a bar structure and perhaps the beginnings of a spiral. But it is not a true spiral. It is smaller, less organized, more turbulent. It has been distorted by the gravitational influence of the Milky Way over billions of years of close orbiting, its shape kneaded and stretched by the tidal forces of its much larger companion. The Large Magellanic Cloud is nevertheless a remarkable place. It contains one of the most active star-forming regions in the entire local group, the Tarantula Nebula, a vast cloud of gas and dust lit from within by the most massive and luminous stars known, blazing blue-white, with an intensity that makes our own great Orion Nebula look modest by comparison. If the Tarantula Nebula were as close to us as the Orion Nebula, it would cast shadows on the ground at night. It would be the brightest object in the sky after the sun and the moon. It would have had names and stories and sacred significance in every human culture that ever looked up. But it is 160,000 light-years away, and so it appears to us as just a slightly brighter region in the glow of the Large Magellanic Cloud, visible to southern hemisphere eyes on a clear night as a small, faint smudge within a slightly larger smudge. The Magellanic Clouds are also connected to the Milky Way by a long stream of gas called the Magellanic Stream, a ribbon of hydrogen gas trailing behind the two dwarf galaxies as they orbit our galaxy, drawn out by tidal forces over millions of years, stretching more than 180 degrees across the sky in radio wavelengths. It is one of the largest structures associated with our galaxy, invisible to ordinary light, but mapped in radio waves. A ghostly trail of gas that marks the long orbital path the Magellanic Clouds have taken around the Milky Way. Like the wake of a boat, but a wake that stretches for 1 billion years and 100,000 light years, and is made of the same primordial hydrogen that everything else in this story began with. The same hydrogen that condensed out of the early universe fog, the same hydrogen that collapsed into the first stars, the same hydrogen that fills the spiral arms of the Milky Way and fuels the star formation that produced the sun and, eventually, this night, and you resting in it. Let your body soften a little more. Let the hydrogen that is in you, in every molecule of water that makes up most of what you are, connect you to that ancient thread. We have talked about how spiral galaxies form and why they keep their shape. But there is another question that sits quietly beside those ones, equally soft and equally profound. How do spiral galaxies end? Everything in the universe changes over time. Stars are born and die. Galaxies evolve. The universe itself is expanding and cooling and will eventually reach states very different from the one it is in now. And so, it is worth spending a few calm moments thinking about the deep future of galaxies, not with any anxiety, but with the kind of long horizon peace that comes from understanding that change at cosmic scales is always slow and always generates something new. In the relatively near future, say 1 billion years from now, the Milky Way will look broadly similar to how it does today. The sun will have aged, becoming slightly brighter as it burns through more of its hydrogen fuel, but the galaxy will still be a spiral, still turning, still forming new stars in its arms. In about 4 to 5 billion years, as we have discussed, the merger with Andromeda will begin, and over the following several 100 million years, the two galaxies will interact, pass through each other, swing back, and gradually settle into a merged system that will likely be elliptical in shape. The beautiful spiral arms of both galaxies will disperse. The organized, flat, rotating disks will be replaced by a more diffuse, spherical distribution of stars in randomly oriented orbits. But this is not an ending. The merged galaxy, Milkomeda, as it has been affectionately named, will still contain hundreds of billions of stars. Many of those stars will still have their planetary systems. Life, if it exists on any of them, will probably survive the merger largely unaffected. The merger of galaxies does not destroy planets or solar systems, only rearranges the large-scale structure. The night sky of any world in the merged galaxy will look very different. No longer the faint band of the Milky Way stretching across the sky, but a brighter, more diffuse glow in all directions, with the mixed stars of both former galaxies distributed throughout the sky. It would be disorienting and extraordinarily beautiful, an entirely different kind of night. On still longer timescales, tens of billions of years, hundreds of billions, the universe's expansion will continue to carry other galaxies away from us. The most distant ones eventually receding beyond the cosmic horizon, moving away so fast that their light can never reach us again. The local group of galaxies, the Milky Way, Andromeda, and their smaller companions, is gravitationally bound together and will remain together even as the larger universe expands. But the other galaxy groups, the distant clusters, will recede and eventually vanish from the observable universe entirely. The night sky of the very far future will contain far fewer visible galaxies, just the stars of the local group, merged into a single large elliptical surrounded by the local small companions, and beyond them, the expanding darkness. But that is so far away it has no grip on tonight. Tonight, the sky is full. The galaxies are everywhere for eyes that can see them and instruments that can find them. The universe is at its richest, most intricate phase, full of structure, full of light, full of spirals turning in the dark. And you are here for it. You are here for the best part. Perhaps someone comes to mind who would enjoy a quiet night like this one. A friend who is having trouble sleeping, or someone who loves space, or someone who simply needs a gentle hour. The channel is always glad of quiet company, and sharing costs nothing. There is a practice among some astronomers, a private, unofficial one, not mentioned in papers or at conferences, of simply sitting with an image for a long time, not analyzing it, not measuring it, not extracting data from it, just looking. A long exposure photograph of a galaxy, printed large or displayed on a screen in a dark room, can hold a person's attention in a way that is difficult to describe. Something between the attention you give to music and the attention you give to a fire. The image is not moving, and yet it seems alive. The spiral arms hold the eye and move it gently along their curve. The bright nucleus glows like an ember. The faint outer regions blur softly into the black of the background. The boundary between galaxy and space so gradual that you cannot say exactly where one ends and the other begins. Some of the most beloved galaxy photographs ever taken have this quality of being impossible to look away from, not because they are dramatic or alarming, but because they are peaceful in a scale that exceeds anything available in ordinary life. The Hubble Ultra Deep Field, an image taken by pointing the Hubble Space Telescope at a tiny patch of seemingly empty sky and exposing for over 11 days, revealed nearly 10,000 galaxies in a piece of sky smaller than a grain of sand held at arm's length. Each of those 10,000 smudges of light is an entire galaxy, containing hundreds of billions of stars spread across distances ranging from a few 100 million to over 13 billion light years. Many of them are spirals, caught in their early youth, when the universe was only a fraction of its current age, their arms still forming, their light now so redshifted by the expansion of the universe that it arrives in infrared rather than visible wavelengths. When that image was released to the public in 2004, it produced something in many people that was not quite surprise and not quite wonder, but something closer to recognition, as though a door had been opened onto something that was always there, that part of us somehow already knew was there, and seeing it confirmed was not shocking, but deeply, quietly satisfying. Yes, of course, the universe is full of galaxies, of course it is, and each one is turning, and each one carries the same physics, the same patterns, the same spiral logic that turns up in shells and seeds and fingerprints. Of course, the universe is coherent, It follows its own rules with perfect faithfulness at every scale, in every place, across every moment of time. That is not a small thing to know. That is perhaps the most comforting thing the universe has ever offered. It is consistent. It is not random. It does not lose the thread of itself. Across 14 billion years and 93 billion light years of observable space, it has been following the same rules with the same patience and producing, with beautiful reliability, the same patterns. The spiral, the density wave, the conservation of angular momentum, the same everywhere. Let that settle into you like warmth, like something you did not know you needed until you felt it. There is a particular kind of stargazing that happens not through a telescope, but simply lying on the ground on a clear night, on grass, or on a blanket on a rooftop, or on the cool boards of a dock extending out over a dark lake, looking straight up at the sky. The Milky Way, in a place dark enough to see it properly, does not look like a photograph. It does not look sharp and dramatic. It looks like a soft wash of light, irregular at its edges, brighter in some places than others, with dark patches where dense molecular clouds block the light of the stars behind them, and brighter patches where star-forming regions and clusters concentrate the light. It looks, honestly, like something painted very gently on the sky with the softest possible brush. You can look at it for a long time without getting tired because there is nothing demanding about it. It simply lies there across the sky, from horizon to horizon on the clearest nights, doing what it has always done. The ancient humans who lay on the ground and looked up at this band of light, and every human culture in history has looked up at it and wondered about it and given it names. We're looking at the combined light of roughly 200 billion stars, most of them too faint and too distant to see individually, their light blending into this soft wash that we have called the Milky Way, the Road of Birds, the River of Heaven, the Silver River, the Way of Santiago, the backbone of night. Every culture gave it a name that emphasized its continuity, its flow, its quality of being something that stretches across the whole sky. Not a point or a region, but a path connecting one horizon to another. And every one of those names was, in its way, correct. The Milky Way is a path. It is the edge-on view of the disk we live inside, the disk of the galaxy seen from within, the flat plane of stars and gas extending outward in all directions from the sun, so that when we look along the plane, we see the accumulated glow of everything in it. And when we look perpendicular to the plane, we see only the nearest stars and then the black of the intergalactic void. We are inside the spiral. We are part of one of those density waves that we have been talking about all night. We are the galaxy looking at itself from a vantage point inside one of its own arms, in a small, quiet bubble of cleared space, on a warm planet, on a soft night, with eyes closed and breathing slow. The Milky Way is arching overhead right now, whether you can see it or not, whether the sky is clear or cloudy, whether there is light pollution or deep country dark. It is there. 200 billion suns making their slow orbits, the bar turning at the center, the arms sweeping outward and curling, the dark matter halo holding everything in its invisible embrace. It is not waiting for anything. It has been doing this for 10 billion years and will keep doing it for billions more. You can rest entirely without worrying about whether the galaxy is managing without you. It is. It always has. If you have stayed with this story all the way to this point, through all the density waves and dark matter halos and Gaia data and globular clusters, then the channel is very glad of your company. And a comment below saying simply that you were here is always a warm thing to find. Let us make our way now toward the final room. Not with any urgency. We will go slowly as we have gone all night, but with the intention of arriving somewhere very quiet, very still, very dark in the best possible sense. The last thing we will think about tonight is time. Not time in the ordinary sense, not the time on your phone or the time until morning, but cosmological time, deep time, the kind of time that makes human history look like a single breath, and the age of the earth look like a single day, and the age of the universe look like, well, like something still young, still in the process of becoming what it will be. The universe is approximately 13.8 billion years old. The Milky Way is approximately 10 to 13 billion years old, formed relatively early in the universe's history, when the primordial gas had already had time to begin condensing into the first structures. For most of the universe's existence, the Milky Way has been here, turning. It has seen the first stars ignite and burn out, the massive, short-lived population 3 stars that formed from pure hydrogen and helium before any heavier elements existed, blazing bright for only a few million years, and then exploding, seeding the galaxy with the first carbon and oxygen and iron that had ever existed anywhere. It has seen generations of stars follow, each generation slightly richer in heavy elements than the last, the galaxy slowly building up its chemical complexity over billions of years of stellar births and deaths. The sun formed about 4.5 billion years ago, when the universe was already over 9 billion years old. By cosmic standards, the sun is not old. It formed in what might be called the current era of star formation, a relatively settled period in galactic history, when the most dramatic early events had already passed, and the galaxy was in a kind of steady, productive middle age. The sun is a population 1 star, rich in heavy elements, born from gas that had already been processed through many previous stellar generations. It would not have been possible much earlier in the universe's history, before enough heavy elements had been made. And Earth, that warm, water-covered world that produced everything you have ever known, formed about 4.5 billion years ago as well, from the disk of gas and dust surrounding the young sun. It has been here for roughly a third of the universe's entire history. The first life appeared here perhaps 4 billion years ago. Complex multicellular life appeared only about 600 million years ago. Modern humans have existed for perhaps 300,000 years. Written history spans about 5,000 years. Your own life has lasted, depending on your age, a few decades at most. And yet, here you are, made of atoms forged in stars billions of years older than the sun, lying inside a galaxy 10 billion years old, on a planet 4.5 billion years old. At the end of an evening in which you have thought about all of this and let it pass through you like light, like warmth, like the density wave that moves through the arms of the Milky Way and leaves new stars in its wake. You are, in the deepest sense, a product of all that time. You are What happens after 10 billion years of a spiral galaxy doing its patient work? You are not separate from the universe's history. You are the most recent chapter of it, the place where the spiral's turning has arrived after everything that came before. And tonight, at this particular moment in the universe's long unfolding, you are resting. Let the atoms rest. Let the borrowed stardust be heavy and warm and still. The galaxy turns for you, not because it knows you or attends to you, but because it has been turning for 10 billion years and will keep turning for billions more. And right now, in this moment, you are exactly part of that turning, breathing slowly in the dark, held by the same gravity that holds the stars in their orbits, part of the same disk, shaped by the same laws, written in the same elegant mathematics as every spiral arm in every galaxy, in every corner of the 2 trillion strong family of light scattered across the observable universe. There is nothing else you need to do. There is nowhere else to be. The spiral is complete, and you are in it, and it is turning, and you can let go of everything except this breath. And then the next one, softer still. And then the one after that, barely a breath at all, just the body doing its oldest and most faithful work, the way the galaxy does its oldest and most faithful work, quietly and without needing to be told. The Milky Way is above you now, whether you can see it or not. Its arms are sweeping slowly through the disk, the density wave moving through ancient gas and sparking new stars at the edges of the arms. Those stars burning blue-white and bright in the spiral for their brief, brilliant lives before cooling and dimming and dying and giving their material back to the galaxy to be used again. The whole system is patient and continuous and deeply, permanently well. It has been going on for longer than you can hold in your mind, and it will go on for longer still. And in the middle of all that going on, there is this, a small, warm planet, a quiet night, a body at rest, a mind letting go of the day and all its weight, sinking toward the deep and ordinary miracle of sleep. Close your eyes all the way now. The story is almost done, but the night is just beginning. Let the spiral arms sweep past. Let the galaxy carry you. Let the ancient hydrogen that is partly what you are remember for a moment the cloud it came from and the long journey it has taken to arrive here. And then let even that dissolve, because you are not the hydrogen anymore. You are the thing the hydrogen became after all this time. And the thing the hydrogen became is resting now, finally, after a long day in a vast and beautiful universe. The stars are keeping watch. The spiral is turning. The density wave moves through the arms of the Milky Way with the patience of something that has never needed to hurry. New stars are being born at this very moment, in molecular clouds you will never visit, their light just beginning its journey outward through space, light that will travel for thousands or millions or billions of years before it reaches anything capable of receiving it. By then, whatever receives it will not be us and will not be anything we can imagine, but the light will arrive. It always does. It is patient. It is faithful. It follows the same path it has always followed, at the same speed, through the same dark, carrying the same information it set out with. And you can do the same. You can arrive at morning carrying what you set out with. Rested, warm, unhurried, held. Sleep now. the galaxy has you.